Hello everyone. For today, we are going to talk about the basic theorems of limits. So, before discussing the first theorem, we have to remember that we are going to deal here with different variables which represent, for example, the c represent the constant and the f and j represent the functions. So, the first limit is the limit of a constant. First, we are going to deal with the limit of a constant. So, the limit of a constant is itself. So, given that we have k, which is a constant here, then the limit of k, in which x approaches to c, is equal to k. So, basically, if we have a constant, if we're going to get the limit of a constant, the limit itself of a constant is a constant. Here are some examples. So, first, we have the limit of 10 as x approaches to c. So, we have to remember that c here represents any constant. So, c can any constant, for example, c can always be 5, 2, or 1, or even a negative integer. So, given that we have the limit of 10 as x approaches to c, the limit itself, as we have remembered in the theorem, the limit of 10 is 10. So in 2, the limit of negative 50 as x approaches to any constant is equal to negative 50. And in number 3, we have the limit of e. So e actually is a constant. So we can say that the limit of e as x approaches to c is equal to e. And so lastly, we have the limit of 4 as x approaches to 5. So here, c represent 5. Here, the limit of 4 is actually 4, not 5. Do not be confused with the limit itself of a constant is the constant itself. So here in this second theorem, the basic theorem of limits, we are going to deal with the limit of x as x approaches c is equal to c. So we have here the limit of x as x approaches to c is equal to c. It's actually somewhat like a substitution. So for example, in example number 1, we have the limit of x as x approaches to 100. So if we're going to substitute the value of x here, which is 100, when we get the limit of x, which is 100. And for the second example, we have the limit of negative 2x as x approaches to 5 is equal to the limit of negative 2 and the value of x, which is 5, and we get the value of negative 10. So the limit of negative 2x as x approaches to 5 is equal to negative 10. So here in example 3, we have the limit of negative x as x approaches to negative 1. We can substitute this negative 1 to the function which is the negative x. So the limit of negative x as it approaches to negative 1 is equal to 1. So for the third theorem, we have the constant multiple theorem. Here, we have the limit of k, as k is any constant, multiplied by f of x, which is the function, is equal to k multiplied by the limit of f of x as x approaches to c is equal to k, which is the constant, and L is the limit of the fx. So don't be confused with the variables that we are using. Fx here is a function, k here is a constant that we have previously used, and the L is the limit. So in this example, we have to let the limit of f of x as x approaches to c is equal to 2. Then if we have the limit of 5 multiplied by fx, which fx is represented by the value of 2, then we have the limit of 5 multiplied by the limit of fx. As we have note here, fx, the limit of fx is equal to 2. So we have 5 multiplied by 2 is equal to 10. And so in the second example, we have the limit of negative 1/2 multiplied by fx as x approaches to c. So we have the limit of negative 1/2 multiplied by the limit of fx as x approaches to c is equal to negative 1/2 multiplied by 2 is equal to negative 1. So our fourth theorem, we have the addition theorem. So generally, it is called addition theorem. However, we can also subtract the two limits of the two functions, or more functions actually. So here we have the limit of f of x plus g of x as x approaches to c. So we have here the limit of f of x as x approaches to c plus the limit of g of x as x approaches to c. And the limit of f of x is equal to L, and the limit of g of x here is equal to m. So we have to sum up the limits of the two functions, and which is represented by the variable of L, and the limit of g of x here is represented by the variable of m. Here we have the limit of f of x minus the g of x, the function of g of x as x approaches to c. We have here the limit of f of x minus the limit of g of x as x approaches, as both limit of the two functions approaches to c. So the limit of f of x here is equal to L, and the limit of g of x here is equal to n. So we have to subtract both the limit of the two functions, which is represented by L minus n. For example, here we let the limit of f of x is equal to 5, and the limit of g of x as x approaches c is equal to negative 20. So for our example number 1, we have the limit of f of x plus the limit of g of x as x approaches to c. So here we have to represent the limit of the two functions, which is the limit of f of x as x approaches to c plus the limit of g of x as x approaches to c. So here we know that the limit of f of x is 5, and the limit of g of x as x approaches c is equal to negative 20. So here we are going to do the operation. So 5 plus negative 20 is equal to negative 15. So for our second example, we have the limit of f of x minus g of x as x approaches to c, which is equal to the limit of f of x as x approaches to c, and the limit of g of x as x approaches to c. So as we have discussed in the previous example, we have the limit of f of x is equal to 5, and the limit of g of x is equal to negative 20. So here the limit of f of x as x approaches to c is equal to 5 minus the limit of g of x, which is the negative 20. So here the limit of the two functions is equal to 25. For our fifth theorem, we have the multiplication theorem. Here we have the limit of f of x multiplied by g of x as x approaches to c is equal to the limit of f of x as x approaches to c multiplied by the limit of g of x as x approaches to c, which is equal to L multiplied by m, where L and m here are the limit of the two functions. So we let the limit of f of x here as x approaches to c is equal to 2, and the limit of g of x is equal to negative 1. So for our example number 1 in the multiplication theorem, we have the limit of g of x multiplied by the function f of x. Here we have the limit of g of x times the limit of f of x, as we have stated that the limit of f of x is equal to 2, and the limit of g of x is equal to negative 1. So we have here the limit of g of x is equal to negative 1 multiplied by the limit of f of x is equal to 2, which is equal to negative 2. For our sixth theorem, we have the division theorem. So here we have the limit of f of x over g of x as x approaches to c. We have here the limit of f of x as x approaches to c divided by the limit of g of x as x approaches to c. And the limit of f of x here is equal to L, and the limit of g of x here is represented by the m. So we have here the limit of the two functions is equal to L all over m. So we have to note here that m cannot be equal to 0. So here our example is the limit of, we let here f of x is equal to -1, and the limit of g of x here is equal to 2, as both approaches to c. The value of x approaches to c. So here we have the limit of f of x all over g of x is as x approaches to c is equal to the limit of f of x as x approaches to c all over the limit of g of x as x approaches to c. So we know that the limit of f of x is -1, so we have here -1 all over the limit of g of x, which is 2. So we have here -1/2. So our limit is -1/2. So for our second example, we let the limit of f of x is equal to 0 and the limit of g of x is equal to 2. So if we are going to get the limit of f of x all over g of x, we have here the limit of f of x is equal to 0, which is we let the function of f of x equal to 0, and the limit of g of x here equals to 2. So we have the limit of the function, two functions, is equal to 0. So for our third example, we let the f of x is equal to 5 and the limit of g of x here is equal to 0. So if we're going to evaluate the limit of the two function, which is the f of x all over g of x as x approaches to c, is equal to the limit of f of x as x approaches to c and all over the limit of g of x as x approaches to c is equal to 5 all over 0, which is undefined. And we can say that the limit does not exist. So as what we have said in the division theorem, we have to remember that m cannot be equal to 0 because our limit actually will not exist. So to our second to the last theorem, we have the power theorem. Basically here you have the function and it is raised to a certain number. So basically we have here the limit of f of x is raised to the p. P here is any constant. So we have here the limit of the function f of x is equal to the limit of L raised to p. So in our first example, we let the f of x is equal to 2 as x approaches to c. So we have here the limit of f of x raised to the power of 3 as x approaches to c. So we are just going to get or substitute the limit of f of x here. We have the limit of f of x, as we have stated, 2, and we let the variable 2 raised to 3, and we get the value of 8. So for our radical or root theorem, for us to clearly understand it, let's deal here with some example. So here we let the limit of f of x as x approaches c is equal to 4. Then the limit of f of x as x approaches to c is equal to the radicand, inside of radicand, the limit of f of x as x approaches to c is equal to the square root of 4, which is equal to 2. So actually in these 8 theorems, as what you have observed, we can actually get the limit of the functions by substituting the value of x. But I think it is also important to really understand the method of getting the limits of the functions. So thank you for listening, and don't forget to subscribe.